Hi guys, this is Miss Nickel, and this video is really just a quick review of Newton's three laws, but I'm tying it back to the elevator problem, which is a classic problem in physics that asks what somebody weighs when an elevator is accelerating up or down. And the reason that this is important because it's a great way to apply Newton's laws and get a better understanding of what they really mean. So Newton's first law says that an object doesn't change its motion unless acted upon by an unbalanced force. So the key word here is unbalanced force. What does that mean? And I'm going to give you an example. So let's say we have a soccer ball that's just resting on the ground, right? Here it is. And this is the ball right here. And so, are there any forces acting on this ball right now? Yes, the ball is stationary, but there are balanced forces acting on the ball. And those forces are the force of gravity, which we call the weight of the ball, which is acting downward. And then we have the equal and opposite normal force, which is acting upward here. And the normal force, just the force exerted perpendicular to any two surfaces that are in contact. It prevents the ball from sinking down into the ground. So we have forces acting on the ball, but the forces are balanced. And since they're balanced, there is no net force, and therefore the ball does not move. But if we have a person who comes along and decides to kick the soccer ball just like this, then we're going to have an unbalanced force acting on the soccer ball, right? And the soccer ball is going to move in the direction of that unbalanced force. And that is really just Newton's first law right there. Okay, now let's talk about Newton's second law. This is the one we're probably all most familiar with. And before I do that, I think I'm just going to get rid of our elevator guy here. I can make him small and kind of move him over to the side. And we're going to get this guy to move too over here. All right, hopefully that'll give me enough room to talk about what I want to talk about. And so we're talking about Newton's second law right now. And you all know that that means force is equal to mass times acceleration, right? So I'll write that out. Force equals mass times acceleration. And you probably also know that we can write that equation as acceleration is equal to force over mass. And this is the version of the equation that I like for a couple different reasons. One of which is that it's really easy to see that if force is zero, then we will have no acceleration. So in other words, if you have no force acting on an object, then it's not going to change its speed or direction. But the force we're talking about in that case is net force. And you have to remember that the opposite is true. If we have a net force, then there will be acceleration. But let's talk a little bit more about what we mean by that net force. So right here, when we had the stationary soccer ball, the forces canceled out, right? So we had force acting on the object, but not a net force. So in this case, we could say that F net, we'll call it, is equal to zero. Okay, so we had a zero net force, which is the same as having balanced forces. So if we are going to have acceleration, what we can say about that is that net force, F net, is not going to be zero. We're talking about a non-zero net force here if we have acceleration, and that would be the same thing as an unbalanced force. Okay, so the other thing that we want to keep in mind when we're looking at this equation, let me just write it out one more time here so I have a little more space to work, is just the relationship between acceleration, force, and mass, which is really clear in this version of the equation. And so we can see that if mass is kept constant and we increase our force, then acceleration is also going to increase, right? And if force is kept constant and we increase our mass, that would be down here, then acceleration will decrease. Okay, and that is what this equation tells us. So that's probably the most important ideas to get from Newton's second law. And now we'll move on to Newton's third law, which is about forces acting between objects. Okay, so Newton's third law is all about the forces that act between objects. It says for every action force, there is a reaction force, and these forces act on different objects. So let's take an example again, and this time we're going to look at the example of somebody pushing a heavy box across the floor. So we'll need a floor, and here's our box. Okay, looks about like this. And so we're going to try to look at the action reaction forces in this scenario. I'm going to put in a person pushing on this box, or we'll call it a refrigerator. And so they're having to work really hard to do this. It's very heavy. So we got them kind of bent over here, pushing, and these are their arms pushing on the refrigerator. Here they are. Okay, so what we're really interested in though are what are the forces that are acting in this situation. And so I'm going to go through the different force pairs. So I'll be drawing the forces with the point of origin at the interaction between the two objects in the direction that the force is going. So we have the force of the person pushing on the refrigerator going this direction. So I'm going to call that a force of person on refrigerator with an R, and the refrigerator pushing back with an equal amount of force in the opposite direction. I think we're all pretty clear on that. And that is going to be the force of the refrigerator on the person. That's one pair. But there are other force pairs in this diagram. I'd like to go through what they are because it's all of the forces acting on the refrigerator that will determine whether or not it moves. So there are also going to be forces acting between the floor and the refrigerator. Because of friction, the refrigerator is going to exert a backward, or the floor is going to exert a backward force on the refrigerator. So we'll draw that on the refrigerator here, and we can label that as force F of floor, little f, on refrigerator, which we're calling R. And then there is going to be an equal and opposite force of the refrigerator on the floor. We know that because of Newton's third law. And so that's going to be the force of refrigerator on floor, just like that. Now, the person wouldn't be able to push the refrigerator if they were sliding backwards. So there also has to be a force between the floor and the person. So the person is going to exert a backward force on the floor. We know that's how we move forward in general. And so that's going to be force of person on floor. And then the floor is exerting a forward force on the person, and that is force of floor on person. So these are the force pairs that occur in this system of objects. It's a simplification, I'm sure, but it gives us the basic idea. So we have the action and reaction forces, but the thing to keep in mind is that whether or not an object moves is determined by just the forces acting on that object. So whether or not the refrigerator moves is determined by the forces acting on the refrigerator. And so if the refrigerator is moving to the right in this picture, then there must be a net force acting in the rightward direction. And that's pretty much what we need to get out of Newton's third law right now. I'm going to be talking some more about some important concepts related to force in my next video. And those concepts are the same as the title of the video, and that's going to be weight, because we know that weight is a force, and normal force, which you can see from the elevator problem, has a relationship with weight. We're going to talk about what that is. And then net force, which we talked about a little bit already in this video, but I want to go over it some more because the net force is really extremely important for everything we're trying to understand with Newton's laws. Okay, so that's all for today. Thanks for taking a look at my video, and I'll be in touch. Bye.